This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 4 of Week 3, Transient Conduction. The Biot number that decides whether you can lump the body's temperature. The lumped-capacitance solution giving exponential decay toward ambient, and the time constant for how fast. Topics 1 through 3 assume steady state, but real problems run on a clock. Quenching a steel part in oil, a thermocouple in a hot stream, cooling a hot ingot, preheating a casting. Temperature changes in time, and how long is the question. Whenever a problem asks how long, or gives an initial and a target temperature, it's transient. Same 3-column shape. 2 new material properties the steady-state topics didn't need: density and specific heat, since storing heat differs from passing it through. Inputs up top, derived in the middle. Characteristic length and Biot number. Bottom row, the time to reach the target. The Biot number is the ratio of internal conduction resistance to surface convection resistance. The Handbook prints the volume form, HV over KAS. Most textbooks prefer the equivalent, HLC over K, where LC is the characteristic length, volume over surface area. These match. Physically, BI weighs pushing heat through the body against pulling it off the surface. Small BI, conduction is easy. The body stays nearly uniform. Large BI, the surface cools fast, but the core lags. Lumped capacitance is valid when BI is much less than 1. Engineering threshold, 0.1. Below that, the body is uniform within about 5% at any instant. Enough to model as a single lump of thermal mass. BI below 0.1, treat T of T as one number. The exponential decay solution applies. At or above, spatial gradients matter. The single temperature model breaks down. Use the one-term approximation or Heisler charts. Always run the Biot check first. Density, specific heat, conductivity, and a film coefficient together signal it. Once BI is below 0.1, an energy balance, heat lost equals drop in internal energy, gives the closed form. The Handbook's rate constant beta is HAS over rho VCP. The time constant tau is 1 over beta rho VCP over HAS, so the ratio is e to the minus t over tau. At 1 time constant, the gap is about 37% of its initial value. At 3, about 5%. At 5, under 1%. Effectively equilibrated. It's a ratio of temperature differences, so Kelvin and Celsius agree. When BI is at or above 0.1, the body has a real internal gradient, and lumped capacitance no longer applies. The exam-level handles, the one-term series approximation, accurate when the Fourier number exceeds 0.2, and Heisler charts for plane walls, infinite cylinders, and spheres. Beyond those, finite element numerics, out of scope. On exam day, check BI first. If it fails, flag the problem as chart required and find the right chart in the references. Worked problem. A 25 mm steel ball at 300 Celsius is quenched in oil at 30. The oil's film coefficient and the steel's properties are given. Find the time to cool to 50 Celsius, first verifying lumped capacitance with the Biot check. Run the Biot check first. For a sphere, volume over surface area collapses to d over 6, about 4.17 millimeters. The Biot number, HLC over K, lands near 0.033, well below the cutoff, so lumped capacitance is valid. The volume form gives the same number, since V over AS is exactly LC. Build the time constant, rho VCP over HAS. Equivalently, rho CP LC over H, about 39 seconds. Rearrange for time, T equals minus tau times the natural log of the temperature ratio, 50 minus 30 over 300 minus 30, about 0.074, giving about 101.5 seconds. Final answer, about 101.5 seconds, roughly 1 minute 42. Units, tau is joules per watt, which is seconds. Magnitude, about 2.6 time constants, and e to the minus 2.6 is our ratio, 0.074. Physical sense, a small steel ball within 20 Kelvin of the oil in under 2 minutes. Aggressive convection on a small ball means a fast quench. Sign, it starts above ambient, cools, so T is positive. 5 traps that quietly cost points. 1. Skipping the Biot check. The exponential decay form is only valid for Bi below 0.1, and using it blind is the biggest trap. 2. Mixing absolute and difference temperatures. The ratio inside the log is of differences, so Kelvin and Celsius agree, but don't mix absolute Kelvin with Celsius differences, pick one. 3. Wrong characteristic length. LC equals V over AS, geometry specific, sphere D over 6, long cylinder R over 2, plain wall cooled both faces L over 2. Use D over 2 for a sphere, and the Biot number is off by 3. 4. Time constant versus half-life. Tau is the E folding time, not the half-life, differing by the natural log of 2. 5. Ignoring Heisler when Bi is at or above 0.1. If lumped capacitance fails, surface and centerline temperatures diverge, so don't use the formula. Bookmark the page. The Biot number criterion and the exponential decay solution sit on the same page. One subtlety, the handbook prints the volume form HV over KAS. While most textbooks prefer HLC over K, they're identical. It also writes the rate constant beta instead of the time constant tau, tau being 1 over beta. Up next, Topic 5, Fins and Extended Surfaces. Topic 4 dropped steady state. Topic 5 puts it back but adds a geometric trick, extending the surface with fins. We'll meet the fin equation, the fin parameter M, the long fin temperature profile, and fin efficiency, asking how much fins boost heat rate over a bare base.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.